4.5 indeterminate forms and Hopital's rule. So indeterminate forms and Hopital's rule. So one form we're gonna take is an indeterminate form. Indeterminate form. Zero over zero. So this is what we're going to be looking at first, and then we're going to be able to get things in terms of 0 over 0. Essentially, it'll work for a couple of our independent forms, or this Hopital's rule that we're going to get to. But let's kind of discuss why this is an indeterminate form. So there's two things that we've seen, something like a over 0. Where is that back here? A over 0 we consider undefined. But 0 over 0 we consider, I'll say equals, but we consider indeterminate. Now, the reason, like, just kind of a quick example of why this is the case is, for instance, if I have, like, 6 over 0, if we call this equal to, let's say equal to b, what we know is division has an equivalent multiplication expression. So what I do is I just multiply both sides by 0. So so that would mean 6 would be equal to b times 0. So if I'm trying to figure out what b is, what I can do is if I can't figure it out here, I can actually try to figure it out here. But we know that this is not going to be true because anything times 0, well, b times 0, assuming b is not 0, but, well, actually, even if it is 0, but b times 0 is 0. So this is false. This is false. So the idea is b is considered undefined, so we'd say b is undefined. It's undefined because there is no number that will make this work, because any number times 0 is going to be 0. That's why b is undefined. But if we have this similar expression 0 over 0, let's call this equal to b. If I write it in its equivalent multiplication, 0 is equal to b times 0. The difference between this equation and this equation is this one's always false. There's no b that'll work. But in this equation, this is always true. This is always true, and that means every b will work. So false. No b works. And this is all of them do. Now I'm trying to talk about real numbers here, but we'll just let b. So we say b is indeterminate. We cannot figure out what it is because they all work. So we're going to look at things that are in indeterminate form, which is 0 over 0. So that reaches our very first theorem. So this is Hopital's rule, but they call this the first form, and then we're going to get into more powerful forms of this. More generalization, I really should say. This is a specific case of the more general rule. So suppose that f of a is equal to 0 and g of a is equal to 0. And f prime of a and g prime of a exist. F prime of a, and lots of ands, I apologize, g prime of a exist, where g prime of a is not equal to 0. Then the limit as x approaches a of f of a, I apologize, f of x all over g of x ends up being f prime of a over g prime of a. So kind of a quick example here would be find the limit. So one of my favorite ones to do is, what about the limit as x approaches 0 of the sine of x over x? Now, in the first section on limits, we basically said, well, this is equal to 1. You're just going to have to take my word for it. And there was some graphical evidence to support this, but this is a real quick way of actually doing this. So what I know is, using this limit, what I can do is I can just take the derivative of the top and the derivative of the bottom and then plug in 0. So what I mean by that is, this is going to be equal, the derivative of the top is going to be equal to the cosine of x all over the, well, my apologies, all over 1 evaluated at x equals 0. So this ends up being the cosine of 0 over 1, which is equal to 1 over 1, which is 1. So that's kind of verification of why that's true. B. The limit as x approaches 0 of the square root of 1 plus x minus 1 all over x. I guess it's all over x again. That's kind of boring. Can I do better than that? All over, let's do this. 3x minus 2. There. Alright, so what it says is, we're going to take the derivative of the top, and then we have to take the derivative of the bottom. Now, remember what we're doing here is, this is a way of finding limits. So we have to be careful of, this is not the derivative of f over g. The derivative of f over g is the quotient rule, f prime g minus f g prime all over g squared. This is just a technique to help us find limits, and we can use derivatives to help us find limits. So, f is its own function, g is its own function, so we're going to take the derivative of the top and the bottom independently, and then keep them keep them as that rational. So, first things first, I know that this is equal to, I can rewrite this as x plus 1 to the 1/2 power, so I know the derivative of that thing is going to be 1/2 times 1 plus x to the minus 1/2 times the derivative of what's inside, which is 1, and the derivative of the bottom is going to be equal to 3, and this is all going to be evaluated at x equals 0. Well, before I plug in x equals 0, I'd like to simplify this. So I know that this square root is supposed to be on the bottom, and same thing with this 2. So this is going to be equal to 1 all over 6, because the 2 times 3, square root of 1 plus x, evaluated at x equals 0. So plugging it in 0, I'm going to have 1 all over 6 times the square root of 1 plus 0, so this is going to be 1/6. Well, it's a really clever way of finding limits, because if you guys are trying to find limits of this expression before, there's certain functions that were complicated. Something like this, you'd have to use a conjugate. Up here, there really wasn't a nice way of doing this. Not something that was simple. Something that maybe that was messy. Alright, so I want the more powerful form. So, second form, or basically the form that we're going to use from now on. So this is the stronger form. So, theorem. You might ask why I didn't start with just this form. Well, the idea is that the first one's to help you kind of get the idea of what's going on here. And this one is to expand that idea. So, Hopital's rule. So, the stronger form. So, suppose we have the same thing, that f of a and g of a are both 0. So, this is going to be in the indeterminate form of 0 over 0. And that f and g are differentiable. On an open interval. Containing A. And so many ends. And g prime of x is not equal to 0 on this interval. Then what we have is the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x all over g prime of x. So we were technically using this. The thing was we were taking the derivatives and then we were plugging in a. So the idea was in the previous exercises, the a and b, this limit exists. The function that spit out after we went to this, the function that spit out f prime over g prime was actually was defined at a, so we could just plug in a. But that might not be the case. So what this allows us to do is just keep applying L'Hopital's rule over and over again until you're no longer in indeterminate form. So an example would be this. Determine the limit. Using L'Hopital's rule. So A, we have the limit as x approaches 0 of the square root of 1 plus x minus x over 2 all divided by x squared. Okay, so L'Hopital's rule says that the limit of a rational is equal to the limit of the limit of the rational f over g is equal to the limit of f prime over g prime. So what I'm going to do is I'm going to take the derivative of the top, and it's going to be on the top over here. I'm going to take the derivative of the bottom, it's going to be on the bottom over here, but I'm going to keep this exact same limit. So this is the limit as x approaches 0 of, well, the derivative of the top. Well, we just went through this. This is 1/2 times 1 plus x to the minus 1/2. And then this is just minus 1/2. That's the derivative of x over 2, because it's 1 over 2x. So that's the derivative of the top. The derivative of the bottom is equal to 2x. Now, before we do anything, we're going to simplify, and then we're going to see what we have to do next. So we're going to simplify this expression. So this is going to be the limit as x over x goes to 0 of man, I'd like to clean this up a little bit. I'm definitely going to clean this up. So this is going to be equal to 1 all over 2 times the square root of 1 plus x minus 1/2. Now what I'd like to do is I want to add all these things together because, well, I guess, I don't think I really have to. Let's just take a look. All over 2x. Well, if you notice, what we have here is this expression is actually still differentiable. Like this, I could take the derivative of the top, and I can also take the derivative of the bottom again. So what I still have is, notice that if I plug in 0, what we get is this is going to be 1/2, because when I plug in 0, this is going to be the square root of 1, which is just going to be 1, minus 1/2 all over 2 times 0. So this is 0 over 0 still. So since it's of this form, 0 over 0 still, what I can do is I can just apply L'Hopital's rule again. So I'm going to take the derivative again. Now I'm going to take the derivative looking at this thing because it's easier to take derivatives when you have powers. So this is going to be the limit as x approaches 0 of, well, looking at the top piece, minus 1/2 times 1/2 is going to be equal to minus 1/4 times 1 plus x, and then dropping this power down by 1 is going to be minus 3 halves. The derivative of 1 half is 0, so that's easy. And then on the bottom, the derivative of 2x is 2. Now again, remember, the derivative of this is not equal to this. It's not even close. You have to use the quotient rule. So, but this is a way to find limits. Now I'm going to simplify this. So this is equal to the limit as x approaches 0 of, well, this 4 can go on bottom, so I have an over 8 on bottom. Actually, this is going to be as 1 all over 8 times the, I'm just going to write that as 3 halves power. It's not that big of a deal. I know it's the square root of 1 plus x cubed, but whatever. So there we go. Notice this is no longer indeterminate. Because if I plug in 0, the top is going to be 1. And the bottom will be 8. So this is no longer 0 over 0. So that means I'm done applying the rule. So as soon as this expression is no longer 0 over 0, when you plug in that number, you are done. Plug in 0 and you are finally done. So when I plug in 0, the top is going to be 1, and the bottom is going to be 8 times 1. So this is going to be 1 over 8. B. Let's do it again. So it's going to be one where I don't have it. Limit equals 0. I'm going to pick a different one. So limits as x approaches 1. This is 1 of x minus 1 all over the natural log of x minus the sine of pi x. All right, so what I want to kind of do is they don't always have to be x equals 0. It says x equals a, so it'll work for any limit. So what I'm going to do is I'm going to check this first. I'm going to plug in 1 and make sure that this is indeterminate form. So 1 minus 1 is 0. Good. The natural log of 1 is 0. And the sine of pi is also 0. So this is 0 over 0. So if it's 0 over 0, we are good. I forgot to actually mention that. We should always verify when we're plugging these particular things in. We should always verify that this is indeterminate form. And I know I didn't really mention it, but like if you do the original, when you plug in 0, this is 1. That's an error there. I'm gonna have to look at that. I will come back. I'll come back to that. Okay, so we should always make sure that this is 0 over 0. So when you plug in 1, you get 0. So now what we're going to do is we're going to take the derivative of the top, we're going to take the derivative of the bottom. So this is equal to the limit as x approaches 1 of, well, the derivative of the top is equal to 1. And then derivative of the bottom, well, the natural log of x is 1 over x. And the derivative of the sine of pi x is going to be equal to minus, well, the derivative, yeah, it doesn't change sign. So this is going to be the cosine of that pi x times the derivative of what's inside. So I'm going to multiply it by the derivative of what's inside. The derivative of pi x is just pi. So this is pi cosine pi x. Now what I'm going to do is I'm going to go ahead and quickly check this to see what we have here. Well, if you plug in the top is 1 and the bottom is, well, let's see. This is going to be equal to, let's clean this up. I'm going to go x over x. So this is going to be the limit as x approaches 1 of 1. 1 over x minus pi x cosine of pi x all over x. So this is going to be equal to the limit as x approaches 1 of 1 all over 1 minus pi x cosine x. So what I did is just top and bottom by x, so I can add these and then plug that in. All over x. So still simplify. I'm trying to put it in a rational form. So multiplied by the reciprocal. That's the denominator. So this is going to be the limit as this big one. X approaches 1 of x all over 1 minus pi x times the cosine of pi. Okay, so what's the cosine of pi? Go back to our unit circle. We know the cosine of pi is equal to -1. We might be good here. Let's go see if we're going to be all right. So this becomes -1, and this is 1. Ooh, let's see, 1 all over 1 minus pi times 1 times -1. So this is going to be 1 all over 1 plus pi. So that's our answer. Now the reason why I know I'm not just going to take the derivative again, top and bottom, is because this is no longer 0 over 0. So it doesn't work unless it does not work unless you are in indeterminate form. See if I think I've written another one. So C. Limit as x approaches 0 of 1 minus the cosine of x all over x plus x squared. So using Hopital's rule, we know this is going to be equal to the limit as x approaches 0. Well, we still got to make sure this is 0 over 0. So when you plug in 0, the cosine of 0 is equal to 1. And if I plug in 0 here, this is 0. So 1 minus 1, the top is 0. Plug in 0 on the bottom is 0. So this is 0 over 0. So since it's indeterminate form, I can take the derivative of the top. Derivative of 1 is 0. Derivative minus cosine of x is going to be equal to the sine of x. And on the bottom, this is going to be 1 plus 2x. Now we really, we have to be careful because a lot of times you just keep going and going and going until you're done. But identifying when you're done is very important. So when do I just keep taking derivative of the top, derivative of the bottom? Well, again, plug in 0. Sine of 0 is equal to 0. But when I plug 0 in the bottom, this bottom is not 0. 1 plus 2 times 0 is 1 plus 0, so the bottom is 1. We're done. As soon as it's no longer 0 over 0, as long as it's no longer 0 over 0, we know we're done. This is 1, this is 0. I'll just erase that. This is 0 divided by 1, so this is equal to 0. So that's why we're done. One-side limits. So when we have our one-sided limits, we have to kind of remember when we did one-sided limits, we were doing those to be able to find asymptotes. So getting infinity or negative infinity is something that's going to show up a lot with your one-sided limits. It doesn't have to. Even if I had the previous problem like this, we could have said this is 0 from the positive side. Even if it was 0 from the positive side, this would be 0 from the positive side, and this limit wouldn't change. The problem is what happens if this was, say, 1 over 0. If you know that the top is a constant and the bottom is 0, you get undefined, and that is it's either it's a whole, which is what this is, or it's a it's a whole if it's 0 over 0. It's an asymptote if it's a constant over 0. So we will notice that a lot of these things are asymptotes. So A, what is the limit as x approaches 0 from the positive side of the sine of x all over x squared? Well, using Hopital's rule, we're going to check to see if it works. Plug it in 0, this is 0, this is 0, so we're good. It's indeterminate form. So I can take the derivative of the top, I can take the derivative of the bottom. So this is going to be equal to the cosine of x all over 2x. And I know I'm done because the cosine of 0 is equal to 1. This is no longer 0 over 0. This is actually 1 over 0. So if the top is a constant and the bottom is 0, we're talking about something that's shooting off into infinity. So we can kind of break this into two pieces if you guys remember that this is the same thing as, remember this is the limit of essentially a multiplication. This is the same thing as the limit as x approaches 0 of cosine of x multiplied by 1 over 2x. So you could pull out the 1/2. This would be 1/2 times the limit as x approaches 0 from the positive side of the cosine of x multiplied by the limit as x approaches 0 from the positive side of 1 over x. Now you know that this one is equal to 1. So this is going to be equal to 1/2 times 1, but what we know is if we look at 1 over x, remember what that thing looks like. 1 over x looks like this and like this. What we know is it has an asymptote that runs right down the middle. So if we approach 0 from the positive side, so if we're approaching from the positive side, this is going to go off into infinity. So that's why this one's infinity. If this said negative, then this would be a negative infinity. And what we know is this is equal to infinity. So I guess let's do that. What about the limit as x approaches 0 from the negative side of the same thing? Well, this is going to be the limit as x approaches 0 from the minus of the cosine of x all over 2x. So this is going to be equal to the limit as x approaches 0 from the negative of 1/2 times cosine of x times 1 over x. So we know the limit of the product is the product of the limits. So limit of a constant is a constant. This is going to be the limit as x approaches 0 from the negative side of the cosine of x. And then this is going to be the limit as x approaches 0 from the negative side of 1 over x. And we know if we approach from the negative side that this is going to go off into negative infinity. So this is going to be 1/2. The cosine of 0 is 0. And this, I apologize, not 0, it's 1. It's 1 times negative infinity. So this is equal to negative infinity. Other indeterminate forms. So other indeterminate forms we'll see is infinity over infinity and infinity times 0 and infinity minus infinity. So things that we need is we need things that are in rational form, okay? So as long as they're in rational form, we can go ahead and we can apply L'Hopital's rule. But if they're in these forms, we have to fix them. We have to turn them into rationals so then we can take their derivatives. So an example. Determine the limit. So the limit as x approaches infinity of, say, the natural log of x all over 2 root x. What we know is that the natural log of x as you go to infinity, our natural log function does this. It goes here and then it shoots off into infinity kind of slowly, but it still goes into infinity. Now we know that our square root of x looks like this. It starts here. And it also kind of goes off into infinity, but kind of like a sleeping parabola. So what we know is that this is going to go to infinity, and this is going to go to infinity. So we're a rational form of infinity over infinity, so we're going to go ahead and apply L'Hopital's rule to this. So this is equal to the limit as x goes to infinity of, well, the derivative of the top is going to be 1 over x. And the derivative of the bottom is, well, remember, you just cover up that 2. The derivative of the square root of x is 1/2 x to the minus 1/2, but when you bring that 1/2 out, it's going to cancel with that 2. So this is just going to be 1 over root x. So now we're going to simplify this expression. So this is equal to the limit as x goes to infinity of Well, multiplying by the reciprocal is just going to make that happen. That this is going to go on top and this is going to go on the bottom. So I'm going to multiply by the reciprocal of this. And what we see is this is, again, infinity over infinity. So this is going to go to infinity. If you plug in infinity, this is infinity. So we're just going to do it again. Limit as x goes to infinity. Well, the derivative of the top is 1 over 2 root x. It's 1/2 x to the minus 1/2. And the derivative of the bottom is 1. Now, I know I'm done doing L'Hopital's rule because when you simplify this, this is the limit as x goes to infinity of 1 over 2 root x. And this is no longer that rational infinity over infinity. This is 1 over infinity. So as x goes to infinity, what we remember is, so note the other one we were talking about, horizontal one. The limit as x goes to infinity of 1 over x is equal to 0. So this is similar form of even like 1 over x squared or square root of x. The power on this doesn't matter. It's still going to 0. So this is going to be equal to 0. Let's see if it changes. That's okay. B. Limit as x goes to infinity of e to the x all over x squared. Now again, if you look at each one of these functions, we know that they're both going to infinity. E to the x looks like this. Shoots off into infinity. So as you go to infinity, this is going to go to infinity. And x squared looks like this. So as you go to infinity, this is shooting off into infinity again. So this is infinity over infinity. So this is equal to, doing L'Hopital's rule, limit as x goes to infinity. Derivative of the top is e to the x. Derivative of the bottom is 2x. And again, you can see that this is infinity over infinity. So doing L'Hopital's rule again. This is e to the x, and then this is 2. And what we know is we can pull out this 1/2 just to kind of verify why this works. As x goes to infinity, pulling out that 1/2, I'm going to have e to the x. And we know the e to the x shoots off into infinity, so this is going to be 1/2 times infinity, which is still infinity. All right, what happens when they're in the other forms? What we need is we need rational form to be able to do this. So if I ask us to find the limit as x goes to infinity of x times the sine of 1 over x. Note that this is infinity multiplied by, well, if this piece goes off into infinity, well, I should say if x goes to infinity, this part right here is going to 0. So we know is we have something that's the sine of 0. And the sine of 0 is equal to 0. So we're of this form. We're infinity times 0. What's kind of strange is you would think that this would still be equal to 0, but that's not necessarily the case. Like, it's not technically infinity times 0. It's something that is reaching infinity multiplied by something that's getting close to 0. So remember, this technically is not 0. It's just getting infinitely close to 0. This technically isn't infinity. This is increasing without bounds. So this notation here is a little misleading. So we have to be careful. Remember, it's not actually going to be 0. It's just limiting to 0. It's getting very, very, very close to it. So close that we basically say it is 0. So what I need is this in rational form, and we do not have that. So what I'm going to do is I'm going to be sneaky, and I'm going to kind of cheat. Notice that oh, that's sneaky too. I'm going to make a quick substitution here. What I'm going to do is I'm going to let x equal 1 over h. What that also means is if I solve this for h would be equal to 1 over x. What I'd like is I'd prefer that thing on the bottom. It's kind of the idea. So if x goes to infinity, notice if x goes to infinity, h is going to go to 0. So notice with this piece here, if x shoots off to infinity, this is the same thing as saying h is going to go to 0. So that's what I'm going to do is I'm going to make a substitution. I'm going to turn all the x's into h's. So this is going to be equal to the limit of h. So if I turn that into h, x going to infinity is the same thing as h going to 0. So this is h going to 0. X is now going to become 1 over h. And 1 over x is going to become h. So this is going to be the sine of h. So what we get here is this is going to be the limit as h approaches 0 of the sine of h all over h. And we know that we can use Hopital's rule. So this is derivative of the top with respect to h is going to be the cosine of h, and the derivative of the bottom is 1. And when you plug this in, this is 1 over 1, which is equal to 1. It's kind of clever doing this substitution here. What I'm trying to do is I'm trying to force something like a rational. There's kind of another way to go about something like that as well as this keeps meaning. Maybe I have too many things saved. Another way to do something like that, to turn something that's not rational into something that's rational, would look like this. The reason why I'm going from 0 plus because I know that this thing's not defined for negative zeros. That's why this is a one-sided limit. All right, so what I'm going to do is I'm going to kind of be clever here. I'd like this thing to be rational, so I'm not really going to manipulate this. What I'm going to do is I'm going to manipulate this. That this is the same thing as x over 1. So this is the same thing as the limit as x goes to 0 from the positive of. If I leave that natural log on the top, what I'm going to do is I'm going to put this in the bottom. But you can't just put it in the bottom because if I just stuck it here, that's not equivalent. Multiplying by root x is not the same thing as dividing by root x. So what I'm going to do is I'm going to divide by its reciprocal. So 1 over root x. Notice that if I was to simplify this, if I want to divide by this piece, it's the same thing as multiplying by the reciprocal of this piece. So these two expressions are equivalent. So this is equal to the limit as x approaches infinity from the positive side of the natural log of x all over x to the minus 1/2. Now I'm writing it like that because I know I'm going to do the derivative. But let's kind of see what happens here. So what we have is we have a form of infinity over infinity. So if we look at the natural log function, what we know is the natural log function looks like this. I just want to make sure it's still in indeterminate form. So your natural log function kind of looks like that. You know, it's asymptotic at 0, so it's got an asymptote here. So if I'm going to 0 plus, the natural log is going off into negative infinity. So right now that's going to be negative infinity on top. Now the bottom, 1 over root x, well this is going to be the same thing as 1 over 0. So this is over infinity. This is over infinity. So I have an infinity over infinity. I'm not really concerned about the sign. So that means I can do Hopital's rule. So derivative of the top is going to be 1 over x, and the derivative of the bottom is going to be minus 1/2 x to the minus 3/2. Now before we do anything, we're going to simplify this. It means I'm going to clean this up. So this is the limit as x goes to 0 for the positive side of 1 over x, and this is going to be minus 1 all over 2x to the 3/2. So what I did is I just put that negative 3/2 in the bottom of this fraction here. So this is equal to the limit as x goes to 0 from the positive side. Just multiplying by the reciprocal of this, so I don't have complex fractions. This is going to be minus 2x to the 3/2 all over x. Whew, okay. When I plug in 0, this is 0 over 0, still indeterminate form. This is 0 over 0, right? Now remember that this is not what it's equal to, okay? This is its form, right? This is its form, because you're not allowed to write that on a test. So what I'm going to do is I'm going to Hopital's rule again. As long as it's still an indeterminate form, I'm just going to keep rocking Hopital's rule until we are done. So the derivative of the top is going to be 3 halves times minus 2. So the 2's are going to cancel. So this is going to be minus 3x subtracting 1 to the 1 half. And then the bottom is equal to, well, the derivative of that is 1. So I knew that we were done after this because the derivative of the bottom is 1. So this is equal to the limit as x approaches 0 for the positive side of minus 3 root x. And when I plug in 0, minus 3 root 0, this is equal to 0. So we're done. Limit as x approaches 0. They like writing zeros. It's their favorite thing to approach. Sine of x minus 1 over x. Notice what we have. Our form here is when you plug in 0, this would be 0. If I plug in 0, this would be 0. So this is going to be infinity. This is going to be infinity. I need to approach it from a direction, let's say from the positive direction. So positive infinity, positive infinity. So what we have is this is of the form infinity minus infinity. Now what you'd hope is that this would be equal to 0, but the problem is these things are not approaching infinity at the exact same rate. One of them, if they are going at the exact same rate, then it would basically be equal to 0. But they're not. This is going at a rate that's trig, and this is going at a rate that's essentially almost linear in form for the bottom. So this is not always equal to 0. Remember that these things are approaching infinity, so it's not a number, so you can't subtract it like you wish you could. So what I'm going to do is I'm going to simplify this. I'm going to use L'Hopital's rule. And notice that I can't use L'Hopital's rule now because I know the limit of the difference is the difference of the limits, but you can't just write this. If you put the limit here, you're going to have infinity minus infinity, which is, I don't know, it's indeterminate. Nobody knows what that is. So what I have to do is I want to turn this into a single rational expression so that I can do L'Hopital's rule. So a single rational expression means I have to have a common denominator. So top and bottom the first by x, top and bottom the second by sine of x. So we're going to have the limit as x approaches 0 from the positive side of x minus the sine of x all over x times the sine of x. Now, let's see if it's still 0 over 0. Yeah, this is 0. 0 minus 0. 0 times 0. This is 0 over 0. So that's what form we have. So we can do L'Hopital's rule. The limit as x approaches 0 from the positive. Well, the derivative of the top is 1 minus cosine of x. The derivative of the bottom, well, that's a product. We've got to use the product rule. Because the bottom is a product. Remember, we're taking the derivative of the top. We're taking the derivative of the bottom. So the bottom is derivative of the first, which is 1, times the second, plus the first times the derivative of the second. Now let's see if we have 0 over 0 still. Cosine of 0 is equal to 1, so the top is 0. All right, when I plug this in, this is 0 because the sine of 0 is equal to 0. This is going to be 0 because this is 0 times 1. So this is still 0 over 0. So that means I'm going to do L'Hopital's rule again. This is equal to the limit as x approaches 0 from the positive side of, well, the derivative of the top, derivative minus cosine is positive sine because the derivative of cosine is negative sine. So this is going to be equal to the sine of x. Bottom is going to be the cosine of x. That's the derivative of this thing. But when I take the derivative of this piece, you got to do the product rule. So plus derivative of the first, which is 1, times the second, plus the first, times the derivative of the second. Derivative of the cosine is minus the sine. Let's see what we have here. Boy, I hope we don't have 0 over 0 again. Top is 0. Well, that stinks. This is 0. This is, oh, we're good. We're good. Because this is 1, this is 1. So this is going to be 0 over 2. So let's pop it in. So this is going to be equal to the sine of 0 all over the cosine. Well, I'm going to say this is cosine plus cosine is 2 cosine. Well, it doesn't matter. Just write it this way. It'll still simplify to be the same thing. So this is going to be equal to 0 all over 1 plus 1 plus 0. So this is equal to 0 over 2, which is equal to 0. So I guess in this case it was 0, but you can't guarantee it, okay? You cannot guarantee that infinity minus infinity is equal to 0. It just happened to work in this case. And that's it for this.